good afternoon, or good morning, everybody, and welcome to the ASME eFest program on additive manufacturing. I really appreciate people coming in from all around the world to visit with us today, and we've got a very exciting panel in front of us. My name is Tom Kerpis. I'm the Chief Manufacturing Officer over at Oak Ridge National Laboratory. I have been a member of ASME since my undergraduate days, and am actually now on the board of governors for ASME. So welcome, and let me just set the stage briefly regarding what we're going to be talking about today. So additive manufacturing, yes, we've got three great experts in the area and some opportunities for you all out there around the world to ask questions. But really, when we start talking about additive manufacturing, again, don't just think about, oh, we're going to print out some plastic parts in our little desktop printer. We now have machines that are putting down steel. So here's a part, and you can see this is a 5-axis machine. It's actually, we're putting weld wire down, so we're building metal parts. We're monitoring it not only with visible light, but with infrared light and different types of infrared light to not only understand the shape, the geometry, but also the structure of the part and so forth. And we're not just doing sort of, again, printing with gantries and so forth. Here's a program that we have over at Oak Ridge called Medusa. And basically Medusa, it's got 3 robots. Each one of these has a MIG weld head on, and then we've got a turntable over here. So we're actually printing the part in real time and putting down, I think it's probably about 30, 40 kilograms of steel an hour on this. So we're actually able to print fairly large parts with this. And again, if I want to increase my production capacity, I stick in another robot or 2. So we've got a lot of flexibility. And even beyond that, I'm sure that you have seen a lot of the printing of structures and so forth. So if you think about something called SkyCam, where in the football, whether it's American football or the European football, everywhere else in the world that we might call soccer in the US, you've got a camera that's being pulled around on cables. We have a similar thing where we've got a print head that's funneling concrete down, that's actually putting concrete down. So this is allowing us to print concrete structures. So really changing how we're thinking about things. We can set this up. There are 4 posts, quarter posts, and then you put a crane up in the center, and you can be printing a structure within about an hour. And it's very large, it's very flexible, and it can really change how we think about putting different structures up, whether it's something like a wind turbine tower base or emergency housing after a natural disaster. So it really can be changing things from small to very large. And so it's a very exciting time in terms of additive manufacturing. And what I'd like to do now is turn it over to our learned colleagues. And we decided we're going to go in terms of reverse alphabetic order with last name. So first on our list, I'm going to turn it over to Lakshmi Vendra, who is over at Baker Hughes. Lakshmi, over to you, please.
Thank you, Tom. Hello, everyone. It's a pleasure to be here. My name is Lakshmi Vendra. I am the team leader for Additive Manufacturing Technology Development Group at Baker Hughes, which is based in Houston, Texas. Baker Hughes is an energy technology company offering products and services primarily for oil and gas sector. I am a mechanical engineer like most of you in the audience and have joined Baker Hughes 12 years ago and have served in various business functions, engineering, research, product development, operations, and supply chain. For the last 4 to 5 years, though, I've been leading initiatives to industrialize additive manufacturing and accelerate its adoption in the oil and gas industry. It's been a very interesting period in my career, so it's quite exciting to be part of this session, and I'm looking forward to the discussion with the audience along with the panel. Thank you.
Great, thanks, Lakshmi. And now we've got Mike Kenworthy from Divergent Technologies. So, Mike, there you are.
All right. Thanks, Tom. So, Mike Kenworthy, everyone, and it's a pleasure to be here as well. I think this is a really exciting session to talk to you about additive manufacturing and developing your careers. My background, actually, I started my career in aerospace. I was with GE Aviation for 14 years in various roles, from project engineering to deploying new technologies and new products. And so some of those product lines included things like ignition systems, new sensor technologies. And then eventually I got into 3D printing when we started deploying it for end use products, not just tooling, putting it in heat exchangers and different thermal management and fluid delivery solutions. Got an opportunity to go over to Honeywell Aerospace and be the chief engineer for additive for Honeywell. Did that for a couple years, and we launched a lot of great products and really made tremendous progress in terms of the approach to quality and how we were going to leverage the technology within Honeywell and all the Honeywell businesses. When I got sort of a virtual knock on my door to come out and try something different. So automotive startup trying to do additive manufacturing. And so that was really a cool experience for me. I've been here about 2.5 years with Divergent. If you haven't seen it, I'd say check out the car. It's the Zinger 21C. And this is the first 3D printed, fully crashable, crash-worthy vehicle. It's got over 400 printed parts in it, including metal and plastic, mostly laser powder bed technology. And that's just the first product for us. What it really is about developing an end-to-end production system with AM.
Great. Thank you, Mike. And last, and again, this is just reverse alphabetic order, but I mean, you couldn't ask for a better title, for Jessie Boyer, who's coming up. He's over at Pratt & Whitney, and he is a fellow for additive manufacturing over at Pratt & Whitney. So, I mean, again, here's a guy who's going to know a little bit about additive manufacturing and how it goes. So, Jessie, why don't you give us a little bit of background on yourself?
Yep, no problem. So, yes, me too. I'm very excited to be here today to talk about additive manufacturing and how my career developed. I'm actually a proud Wolverine, graduated from the University of Michigan back in 1994. I was the third generation in my family, 17th person to go to U of M, so I bleed blue. Sorry for all the Ohio State fans out there, but I'll answer any question equally, no problem. I got a degree in naval architecture and marine engineering and one in aerospace engineering. I started my career in manufacturing with automotive, so I worked with General Motors for about 5 years. Started out as an industrial engineer, moved on to a process engineer, and then started my digital career in metrology. So that's inspection. And I was a metrology supervisor. I then moved over to Pratt & Whitney, which is part of Raytheon Technologies, used to be United Technologies. And I started as a CMM programmer. So again, I had quite a bit of background in quality and quality systems. I've been at Pratt for about 20 years now, moved on to a technical leader, supervisor. I was actually the fellow for advanced manufacturing metrology. So I got to work a lot in non-contact scanning, in CT scanning and non-contact scanners, laser line scanners, white light, blue light, things like that. That's where my passion started for additive and things digital. So then I became fellow for additive. I've been the fellow for additive for about 6+ years now. I've been doing additive for about a decade plus, and Pratt's actually been doing additive for about 30 years, right? So we talk about this new, great, wonderful technology. It's actually been around for a long time. What is new and great and exciting is we're starting to do things in metal, like Michael talked about, and Lakshmi as well. So I'm really excited. I have a background in standards committees, so places like ASME, ASTM, and things like that. And I actually have, I do a little bit of teaching on the side, so not at Michigan, now at UConn, but I do some instruction in manufacturing methodologies, right? Conventional as well as additive. I'll just end with, I got 4 kids, ranging in ages 17 to 24. So this is near and dear to my heart, where you guys are coming from on some of these career discussions. 3 girls, 1 boy, and I have obviously coming from Michigan, I have a passion for football. So that's about all I have. I'm excited to hear some of the questions.
Great. Thank you, Jessie. And just sort of, before we get going, of course, I already see one question up in the question and answer window. So make sure you do send your questions over to us. But, as Jessie said, and actually we heard also from Mike and Lakshmi, the reality is this is a very hot new area. It's not just about geometry. There's a lot of great material stuff going on, sort of mixing and matching material, doing it in metal. And really, it's on the manufacturing side, it's on the R&D side, even on the policy side. So this is one thing, and you heard about standards. So in fact, actually, I've spent some time on the Standards Council at ASME. So that's a big area where ASME is engaged. But even the other one, we really have a lot of input. We've had several briefings for Congress and so forth. Over in Washington, D.C., we actually have a manufacturing federal fellow right now who's working, I believe it's with Senator Rubio's office. So, for all of you people out there, there are great opportunities across the board, so make sure you do stay plugged into ASME for, standards opportunities, technology opportunities, but also an opportunity to take your technical skills and help to apply them to policy so that, for example, the nation might move forward in the appropriate direction. So let's shift over. So we've got one question, only one question right now. So there's an opportunity for you to get your questions in there. And it's a good one. We always love to hear this one. How does additive manufacturing vary for zero gravity? Anybody want to take a shot at that one?
Sure, why not? I mean, it's a great question. So the way to think about additive manufacturing, I think, is it's not one technology, it's actually a whole family of technologies. So really what we're talking about with an additive process is it's digital manufacturing, it's materialization of a design concept, piece by piece, matter by matter, and then building up a structure. So when you think about a zero gravity environment, you probably don't want a lot of powder floating around. That would kind of be problematic. So you'd be looking at something probably more like, the technologies that Tom was describing. You'd be looking at a directed energy deposition or an FDM type process. There's some interesting kind of hybrid metal, sort of like a binder jetting process, but with this kind of a wire-based process. Some interesting stuff in that area. So you will have to adapt the technology, but the basic principles for space and what we're doing, here for terrestrial manufacturing really aren't too fundamentally different. So a lot of those skills apply.
And I would just add a couple of things, right? Yeah. So we do, like Michael said, not a whole lot changes, right? But in additive, we are building layer by layer. So things you got to think about is how do you support structures? How do you support a layer below it and things like that? In zero gravity, that takes a little bit different focus, right? You don't necessarily, you don't have that gravity to deal with. The other thing is microstructure does change slightly in that zero gravity. So how can we get different microstructures and things of that nature when we're printing in space?
Yeah, I'll actually just follow up on that. And in fact, when the metal one that I was showing you, where we're actually doing welding, you really rely on gravity for that material to go down. So in essence, it may be a little bit, you're gonna have to think differently about printing in zero G. And then the other one is if you're doing powder, imagine all the powder and so forth that could be floating around to contaminate, let's say, your spaceship and so forth that you have to deal with. So so there are pluses and minuses, but that's a great question. Hey, so here's one, and let me fire this over to Lakshmi since we haven't given you a chance yet. What skills do I need as an undergraduate engineer to pursue additive as a career?
Well, so additive, again, as Michael and Jessie mentioned, it's a group of technologies. It's an emerging technology, so there is a lot of opportunity to learn. So I would think I would put this curiosity and willingness to learn new technologies as the topmost skill that you need to have. There's a lot of opportunity to contribute as well, because there's going to be new materials that are going to be printed, not just metals, not just plastics. There are composites, ceramics, a lot of new groups of material families that are coming into this additive manufacturing technology space. So a great opportunity to leave an impact, learn as well. So anybody that is interested in taking on those challenges, and of course, we need this emerging workforce to come into this emerging field as well, so they can make a meaningful contribution, make an impact, and have a rewarding experience.
Good. And I think that it makes a lot of sense. So again, a lot of what you're learning, in the big areas, but I agree, it's going to be a lot of the materials. In fact, actually, just as a follow-on, there's a great question out there. So after metal, and I think Lakshmi, you hit on some of it, but I'd like to hear from everybody on this one. If you have some thoughts on it, what are some of the next materials that would be helpful to print?
I guess I can start. Refractory alloys is something that we'd like to take a look at, right? So things that are difficult to weld, right? Typically, when you talk about metal, you talk about additive. Even on the plastic side, it's things that can be joined easily. It's kind of a welding process on steroids, I'd say. So when we talk about materials, there's certain materials that are difficult to weld, but yet bring us different material properties, a little bit different applications. So when we get to these refractory alloys, we get to ceramics, things like that, we got to come up with different ways of handling it, different types of process parameters and things like that. So I think those are the ones that we tend to get most interested in. I would like to say one last thing about the skill. The other skill that I think needs to be developed or looked at too is an open mind. Right. One of the things I love about the people coming out of the university and coming new into the workforce is they're not typically burdened with 30 to 40 to 50 plus years of optimizing to a conventional manufacturing process. So it's really the design. How do we design differently? How do we think about parts differently and components? So an open mind. So Lakshmi hit on it, right? You know, you got to be flexible, but also keep that open mind and going with that. So I'm good for that one. I'll let Michael or Lakshmi answer.
No, I fully agree, Jesse. I think, you know, additive manufacturing really is, as a fundamental approach, affects all material systems. You know, most of the initial work was, you know, with the plastic systems, and then they kind of moved into the binder jetting systems with that original, you know, the can't remember the exact name of it. I think it was like a Pro Metal or something like that from X1, where they were binder jetting steel. And then you've also seen a lot of binder jetting and other technologies, SLA type processes for ceramics. So really kind of whatever you want to get deep in and digitally manufacture, there's an opportunity. You know, I'm personally kind of excited, just like Jesse, about these, you know, refractory materials. I think there's the ability to sort of selectively place those onto other surfaces and really get, you know, some advanced properties and unique engineering characteristics that we haven't necessarily had the opportunity to do in engineering up to this point too easily. So also, if you think about, you know, manufacturing of active components, you know, you're going to need multiple material systems. So you got to think about ceramics, you know, our ability to deal with metal oxides, multi-material systems. You know, real products are generally multi-material, right? You know, useful assembly. So, you know, how we're going to bring those together in an AM environment is going to require a lot of different skill sets. And it can't just, you know, be all metal system or all plastic. You're going to need a combined solution.
Great.
Absolutely, absolutely. And Jesse hit on a good point about design for additive. So we have the backlog or a burden to relearn how to design for additive because we are already fine-tuned to conventional manufacturing or subtractive manufacturing technologies. This people coming out of the universities can learn how to design for functionality. So design for additive manufacturing right away so they don't have to relearn it once they start designing products.
Great. Great. So I'm going to ask this sort of a little bit more of a narrow technical question, and then we're going to step back and take a couple of bigger picture questions. But I thought this is really quite nice because it's a nice application. So thoughts on hybrid manufacturing, which would be the combination of additive and subtractive for services such as repair for turbines or engine blocks. I figure we have automotive, we've got aerospace and so forth, and we've got some people who have done a lot of applications. So whoever would like to kick off on that in terms of the repair area.
Yeah, I can take that.
Great.
Not just the aerospace and automotive, even in the oil and gas sector, we have a lot of applications for repair. For example, one of the biggest projects that we're working on is repair of drill bits. So we have the possibility to repair bits that come back from the field so that we are making them back into their original shape and form. So we are increasing the life of the bit. And so this is definitely a big economic benefit that we can provide with additive manufacturing repair.
Yeah.
Great.
Yeah, you are on mute.
Go ahead, Michael.
Okay, I was just gonna. I'm sure Jesse has a lot of great aerospace examples. You know, from repair of turbine blades. You know, repair of a shaft. Let's say a shaft is damaged. I mean, a lot of these technologies were really actually focused on these repair type applications, and fundamentally, those repair applications are often a hybrid process. You have a large machined part, and you're building up a structure on it, and then maybe you need to do some additional finishing depending on how much of a near net or net shape process you have. So really AM kind of grew up in that repair environment and has a lot of its roots in thinking about manufacturing in a hybrid, in a hybrid way. So absolutely, there's an abundance of, you can find a lot of great repair examples, do some research online. There's a tremendous array of applications of AM in real kind of industrial settings and end use applications, including repair.
Cool. Jesse.
Yep. So Michael kind of hit on it. So, we talked about additive being around for about 30 years, right? So, and the other thing I'll say, right? So the repair side of it, is typically called cladding. So cladding's been around for a long time, fixing turbine airfoils and other things. Where additive really gets the semantics on additive is that it's using a computer-aided digital file to do the additive manufacturing layer by layer. So that kind of gets it a little bit more defined from coatings and other processes. But in general, hybrid additive manufacturing is great for that repair side of it. Like I said, not being true additive, it's been around for quite some time, doing weld repairs and requalifying surfaces on turbine airfoils in other cases and other things in aerospace. So it's definitely been there for quite some time.
Yeah, and I'll just add that it's sort of the same thing, let's say on ships and so forth, where we've got propeller repair on large ships. You've had for quite some time people coming in with big welding operations, putting material down, then machining it or removing that material back. So that works out quite well. But I think that as it moves forward, we're going to get better at it. It's going to be more precise, and you're going to have much better control. I do like that. Let's shift to a little bit of a bigger picture question here. And so this one is going to, I think, take some chewing on it. But the question is there a possibility for a circular economy approach to additive manufacturing? Can we reuse materials in additive manufacturing to lengthen their lifetime as products and eliminate waste?
Yeah.
Absolutely. I mean, you want to go ahead, Jesse?
Nope, go.
Okay. Actually, I should talk a little bit about, my company and what we're doing. Actually one of our company sort of vision statements is planet saving manufacturing. So this is a fantastic question. We think deeply about the economics and energy intensity of manufacturing. Fundamentally, that's why we decided to go and try to develop this digital production system, because if you think about the automotive industry, and you can, I think this would be of use for everyone on the call, would be go look up an article by Sergio Marchionne. He's the late chairman of the FCA Auto Group. He called it Confessions of a Capital Junkie. And he talks about how, there hasn't been a return on capital in the auto industry, as far as he was concerned, ever. Even the largest programs aren't really making return on capital. So there's this massive investment in these fixed assets and design specific assets. And what additive manufacturing fundamentally does is it's a flexible and adaptive manufacturing technology where you don't have design specific tooling, hundreds of $1 million of tooling to make an average car, stamping body panels. So we're talking about fundamentally less waste in that way. Now, you really have to think about your different AM technologies versus other primary manufacturing methods. They are energy intense. There is these waste loops, and actually, Tom was making some points about the breadth of additive manufacturing, all the scope of that. There's a huge opportunity in quality and environmental health and safety, and thinking about the recycling of these materials. There's lots of exciting companies focusing on that, like Mollyworks and 6K. So you have to think about the whole end-to-end product chain to really deliver this vision of a circular economy and the ability to recycle these structures. But fundamentally, with most of these materials, they are fully recyclable. Think about aluminum; it's infinitely recyclable. You can take those aluminum structures that you printed at the end of their life cycle. You break them down. You maybe have to modify the composition a little bit, but you can reatomize that material and put it back into a printer. I think that's going to be the way in which you can localize and circularize the manufacturing economics instead of having these massive, global centers. It's going to be more distributed, more localized, and more circularized around these urban centers.
Good. Thanks, Mike. Anybody else want to comment?
I would just add a couple things, right? Michael did a great job explaining it. But from a plastic side, right, we're talking about PLA, which is kind of it's a somewhat biodegradable process made out of organic material. You got ABS plastic, things that we use day in, day out. So on the plastic side, those things definitely can be recycled, like Michael talked about. There's even processes that are taking that material and then chopping it back up again and trying to reuse it as a material extrusion. On the metal side, right, we use powder. We actually reuse the powder multiple times. So, the whole idea with some of these is that we reuse it, significantly to where at some point, right, it does degrade too much and we have to then potentially recycle it. It's trying to make that recycling cost effective. And that's what there are several companies out there trying to do that. Things like the weld wire, right, that's pretty much zero waste, except if you have to machine it off, right? But that weld wire is going around in a bead. That is the bead, that's the final material. So fundamentally, additive is relatively close to zero waste. That's what it's always been touted as. There are some realities that may not be as close to zero waste, but it definitely it's already starting to get to that point.
Good.
Good. I'll just add one comment to what Jessie and Michael already mentioned. One of the biggest advantages with additive is part consolidation. So in conventional manufacturing approach, we have a lot more components with this design for functionality that we get with additive. We don't have to have all those. We kind of simplify the product. So we are cutting out a lot of the small components, the supply chain to source them, to manufacture them, tooling for those components, everything is eliminated. And even the inventory, physical inventory is eliminated because all we have is a digital model. So we are moving towards a digital inventory. So that's reducing a lot of waste.
Sure. I mean, in fact, you could imagine, you could think about with the whole COVID-19 scenario and so forth, yeah. If we had parts for respirators that were, people talk about, well, we have a stockpile, but you could have a digital stockpile. This is what we talk about now. I think it's great. And then that could be distributed even to local or regional manufacturing operations to produce those locally or regionally. I mean, that's great. Shifting to another question, and this is sort of interesting. So how can Mechatronics be involved with additive manufacturing? And when I think about Mechatronics, I'll just sort of throw out, well, what about integrating sensors or actuators or maybe, conductors or heaters, whatever it might be? I'll turn it loose to you, and then I'll talk about a couple of things that we do also have going on over at Oak Ridge in this area.
I guess I'll start. One of the things, right, one of the processes is direct write. So we're actually printing sensors in that on flexible materials or on material extruded materials, right? So there's already an additive process out there that drives some of this mechatronics. And there's actually additive processes that get close to the nanoscale, right? You even think of lithography as not really additive per se, but it's a layer by layer process. So yeah, like Tom says, right, there's plenty of opportunity to help monitor the process. So the machines themselves, as well as create product and parts that would integrate mechatronics going forward.
Yeah.
So, yeah. I think Michael was going to talk as well.
Yeah, sure. I know Tom's got some great stuff on this topic, so I'll be brief. But fundamentally, these machines got to get a lot smarter, right? So there's huge opportunity for people focusing on mechatronics to look at process monitoring, using that process data to develop a better process. You talk about machine learning and these artificial intelligence trends. Someone's got to get them that data, design a system that can take that data and use it and feed it back into the system to make a better part or to correct an issue. Closing the loop on that process, that's the exciting thing for me about additive manufacturing, is having worked with so many open loop processes over my career. There's this opportunity to take additive from that open loop, kind of current state to that vision state of actually truly having a closed loop system. And mechatronics is going to be key to delivering that.
Right. We, for example, over at Oak Ridge, I showed that concrete printer. Well, look, concrete is actually, it's not too bad, right? So you can actually embed a lot of types of sensors in there. I mean, when you're doing the molten steel or titanium with your welding systems, a little bit harder. But in the concrete, we actually can embed that, and we can monitor the curing process and the whole bit as we go along. So I think that there are tremendous opportunities there. But even we've got what's called the BAM, the Big Area Additive Manufacturing for polymer. We are extruding conductors, so wires right through that to even connect up with the sensors and so forth. So I think a lot of good opportunities are coming along the lines, and additive will be enabling it. Great. All right, let's see here. There was a question. I thought it was a pretty good question. It was about sort of additive, anything going on with additive at a micro or nano level. And I know we've had some allusion to that. And I'll just kick it off. It's sort of like on the machining side, right? When you're doing a lot of roughing and so forth, you have it's a little bit lower precision, but you're getting a lot of material removal. When you want to get a really precise part in your machining, you take very light cuts and so forth. So we can, we can get atomically thin layers coming down when we're adding, but it takes a lot of atoms to make up even a millimeter, right? So it's just something to think about. But I'm wondering if any of our colleagues out there, if you have some thoughts in terms of what some of the cool stuff are. I know, Jessie, you mentioned sensors and so forth on the microelectronics side. Fire away.
Yeah. So just recently, right, I've seen a couple that are additive on the nanoscale. Someone printed the Starship Enterprise on a nanoscale. So they're out there. I'll be honest, I don't have a whole lot of experience with it. Not a whole lot of our parts are on the nanoscale, but it's out there, right? And there's definitely people looking at it. With anything else, right? And I'll just kind of put some of the reality in is the inspection process. So yeah, we'll be able to print on the nanoscale. We're going to be able to inspect on the nanoscale. And how well are we going to be able to inspect on it? Maybe it'll be easier because it's only atoms, right? We're at the atom level, but who knows? So it's out there.
Great.
The only thing I might add on that, Tom, I think, this is a topic I would definitely go research if this is exciting for you, but, I watch it because I'm really interested in like this bioprinting kind of, theme and the ability to use, some of these different, kind of systems like viruses to deliver material at these sort of micron scale. There's just going to be a huge explosion in this area over the next 20 years. So if you're planning your career, you want to be get into it at the right point on that S curve, right? Most development follows kind of an S curve. That could be, if that's really exciting for you, that would be something I would dig in on and do some research. There's these different kind of 2-photon lithography techniques. There's probably a lot of techniques people haven't even come up with yet. So there's really huge foundational opportunities to develop these technologies in your career if you want to pursue that.
I agree. I think it's really, it's coming down the road in the whole bit, and there are lots of opportunities. And again, stepping back a little bit now, there's a really nice question about, how AM is impacting the existing manufacturing value chain. I suspect, Lakshmi, given what you do, you probably have some good thoughts on that one. Would you mind kicking this one off?
Sure. So one of the biggest reasons for us in oil and gas industry to get into additive manufacturing is the simplifying the supply chain. The two benefits that we always mention and demonstrate to our customers is lead time reduction. And you might think that it's not very extremely beautiful or attractive to look at as an advantage of additive manufacturing, but it is. Lead time would actually stall our products getting into the field. So any way we can reduce the lead time, and then I'm talking about months to days and weeks with additive. Lead time reduction is a huge benefit and a huge advantage when we are deploying additive for producing parts. And also simplifying the supply chain itself. I already mentioned about it, how we can consolidate the parts, how we can redesign parts that we produce for oil and gas services with additive, where we can actually not be constrained with manufacturing limitations that are possible with conventional manufacturing technologies, and think of new ways we can produce this. And then as we already talked about, it's not just powder bed fusion. We have directed energy deposition. We have different kinds of feedstock we can use to produce this. So there's a lot of optimization going on along the whole value chain, starting from feedstock to design to the process itself, how we can manipulate the process parameters to get the desired performance we want. And this is an opportunity that additive manufacturing lends itself naturally. We can monitor the process layer by layer. We can change or engineer the microstructure. There is an opportunity to do that and then get the desired performance we want from any material. You can change the chemical composition of the powder itself to again affect the mechanical performance. So a lot of opportunity to change how we approach this whole manufacturing aspect for us, especially in the oil and gas.
Great. Jessie, go ahead. I see you've unmuted.
Yep. I'll just add one more thing to it, right? One of the things that's helping with disrupting the technology or the supply chain is we love competition, right? In aerospace, we tend to we get hung up in raw materials, and we get hung up in casting suppliers as well as forging suppliers. So additive brings another area of raw material supply chain, and helps disrupt on the competition side. So in general, yes, what Lakshmi talked about, consolidating the supply chain, minimizing all the little feeders in and out, that's definitely a reality. But also just bringing on additional competition within the suppliers is good as well.
Great, great. Well, thank you. No, I think that's pretty good. Here's a question, and there are sort of several questions along the same line. I'd be very curious to hear from everybody on this one. I'll also throw my thoughts in on the end, just sort of depending on how this goes. But basically, there's this question of, hey, which additive process is going to dominate? Which one's the most versatile, and so forth? And who's going to take over? Everybody smile there. Feel free to. So, Lakshmi, you've got the biggest smile. I'll let you go first.
Okay. So we know that powder bed fusion, laser powder bed fusion has been the most predominant or most mature technology within the additive family. But there are others that are catching up. Jessie mentioned binder jetting. Binder jetting is a huge one, and then directed energy deposition, hybrid manufacturing. So we are seeing there's a lot of applications, there's a lot of opportunity. And of course, I don't want to limit just mentioning a few of them, because there are still a lot of technologies that are just emerging. Somebody asked about nanoscale. Yeah, maybe there is an application for nanoscale. Nano jetting fusion is something that I read about. So there are several, but the most mature technologies so far have been the laser powder bed fusion and directed energy deposition. And I know binder jetting is catching up.
Good. Yeah, Jesse, and then we'll go to Mike, because I definitely want to hear everybody's thoughts on that. Then I'll give you my thought.
Yeah, so don't forget about material extrusion, right? That's the plastic side of it, right? That's been around for quite a bit, and that's invaded pretty much every school and an educational platform that's out there. So I look at them as all tools in the toolbox. I don't think there's anyone that's gonna win out. So it depends on your industry and your application. So when you look at the additive industry as a whole, I don't think there's one that's going to be predominant. It depends on what you're doing. So directed energy, they all got their pluses and minuses. Directed energy deposition can help you out with material properties. It can also help you out with scale. Powder bed fusion, you start to get limited somewhat on size in some of the material properties. There's just physical limits to grain size, grain structure. So binder jetting, again, Lakshmi, you're dead on, right? And you get out of the non-weldable materials with the binder jetting, because you can kind of lay the powder in, you do a semi-sintering, and then you can do some post-processing that's specific to it. So I don't see any one of them. I see them all somewhat maturing. I see them all starting to get better at what they do, and we start to find out where their true niche is and where they're most cost effective going forward.
Good. Mike, any thoughts on that?
No, great answers. I think about these different AM technologies mostly in terms of materials. What am I trying to make? What properties does it need to have? And how does that manufacturing process allow me to maybe do something unique in terms of the properties? And so for me, laser powder bed fusion right now, it's this micro welding process. It's got these super high cooling rates. Right, so we're able to make some unique materials with that approach, get a lot of interesting precipitates and things happening at the nanoscale, and get a unique set of properties that you couldn't make with any other process. And I think that's driving a lot of the growth and adoption with this. Also, just the ability to make a material that has the right defect structure with the right properties. It's currently the one that's sort of giving you the overall best combination of fatigue and whatnot. But you got a lot of other technologies, as Lakshmi said, that are sort of right behind it. They may be better for certain material systems. You think about binder jetting and steel. Steel has a lot of it's tremendously it's almost ideal for that process, because the ability to sinter those materials and get good density. So I don't think there's going to be any one winner. It's really a toolkit of technologies to make the materials that are needed to make, products that are ultimately better and improving over time. And same thing. I also don't think, AM is going to take over all manufacturing anytime soon either, right? Casting and wrought materials and carbon fiber. I mean, these are all going to be relevant. We didn't talk much about carbon fiber. Those technologies are going to be relevant, pretty much forever, right? So you got to use the right AM technology for the problem you're trying to solve, and laser powder bed fusion's a little bit farther along on its S curve, and you want to be aware of all those different technologies, and pick the one you want to invest in and become an expert in, and go deep.
Yep. And so I'll just sort of wrap up on that one. Is basically it's almost like saying, well, what machine tool is going to dominate? Milling, turning, vertical, horizontal. Look, they all have their different areas. I agree. The one thing I find interesting is the powder ones. There's always post processing, and with powder, you've got a lot of respirators, and you've got potentially there could be explosive powders and so forth. With some of the wire ones, they're much easier to deal with and so forth. But again, I think it just depends on what area you're looking at. So we're just about to wrap up, and we do have one question. Sort of, what's more important, to be good or to be passionate? And so what I'd like to do, we've got about 3 minutes. So maybe everybody could just take 30 to 45 seconds. We'll start with Jessie, then Lakshmi, then Mike, and just again, in your opinion, what's more important, to be good or to be passionate? As we're talking to our young career, early career professionals over there.
Yeah. So I'll try to wrap it up relatively quickly. It's a philosophical question. To me, I like the idea of being passionate. And the reason why I say I like being passionate is usually becoming good follows that. So if you're passionate, you're gonna really drive and strive hard to find out all those little nuances. I'll tell you, I wasn't an additive expert by any stretch of the imagination when I first started. I was a digital guy, right? I was a metrology guy, and then they talked to me about building parts with layer by layer. But it's not hard to get passionate about additive. So I think being passionate will drive your curiosity. Your curiosity is going to drive you getting better at what you do. And we all fail, right? So don't be afraid to fail. We used to have a leader that said, fail fast, fail often, fail fast, right? You always can recover, and you got to learn from those failures, right? So you got to understand the risk. Don't fail on the big stuff, right? But you got to understand the risk and go ahead and move quickly. But I think it's passionate, and then the good will follow.
Good deal. Thank you, Jessie. Lakshmi.
Absolutely, I agree there. We are in the midst of a fourth industrial revolution, so definitely be passionate, especially in the field like additive manufacturing or any kind of emerging technology that you're looking at. Good will be a byproduct anyways if you're passionate. So be passionate, take on challenges, because this is a time for you to take risks and bring your enthusiasm to solving these challenges that we have. So definitely be passionate.
Great. Thank you, Lakshmi. Mike.
Yeah, I'm going to make it 3-0 for passionate. The way I think about it is in your career, you're going to run to a lot of different types of people. They're going to have different opinions, backgrounds, perspectives. The passionate people are the ones that are going to be, the gel that really pulls that team together and enables it to do great things, right? So you don't have to be the technically smartest person in the room, know the answer to every question to be a great leader and to drive a team to accomplish, amazing things. So I would say be passionate. That passionate should drive you to, build that technical depth, build also those other skills that people like to talk about, hard and soft skills. You should be passionate about those too, because the way I think about success is, it's usually not delivered by any one person. Sometimes these things have a figurehead and they get a lot of disproportionate credit, but it was really a team effort. None of them did it by themselves. And it's about having a group of passionate people with the right skill sets, putting all those pieces together. That's what's going to make you successful in your careers and enable you to go from successful product, and project to successful project over and over again.
Great. Well, thank you, Mike. Yeah, I'll tell you, basically, if you look out there, you're going to see two types of bosses or leaders out there, those that hire people smarter than themselves and those that don't. And I can tell you which ones are going to be successful. The other thing, if you're the smartest person in the room, you're probably in the wrong room. And what I can tell you from this panel right here is I'm in the right panel. So with that being said, I want to thank our panelists for participating. Look, it's a Saturday. Thank you so much for participating. We had a very good number of participants. All of you out here are spending your Saturday with us for eFest. Thank you so very much. And we'll wrap up the session, and then it'll be time to head over to the next round of sessions. So thanks again for your participation.